In this video, I'd like to do a short demonstration of the Heat-kubernetes templates. These templates are available from the URL you see on your screen. Here we're looking at the contents of the Heat-kubernetes repository. The file kubecluster.yaml is the main Heat template. This describes the Kubernetes master server, as well as the autoscaling group that contains one or more Kubernetes nodes, which are described in the file kubenode.yaml. Let's take a look at kubecluster.yaml. The first major section of this document is the parameters section, which provides inputs to the template. While most of these have reasonable default values, a few must be specified explicitly. SSH key name is the name of an SSH key pair that you've loaded into Nova. Server image is the name of a glance image that will be used to create your Nova instances. This should be an atomic host image from either Red Hat, Fedora, or CentOS. The resources section describes the resources that Heat will create for us. There are a variety of network resources: neutron networks, subnets, routers, and security groups. There's a large collection of software configuration snippets. These are shell scripts or cloud config documents that are ultimately passed to CloudInit as a multi-part MIME archive. CloudInit will use this information to perform initial configuration of the Kubernetes master server. This is the Nova server that will be the Kubernetes master and its associated networking resources. This is followed by the autoscaling group that creates the Kubernetes nodes. The remaining resources are primarily concerned with Heat's autoscaling policy, and we're not going to look at those in detail right now. The last section is the output section. Of particular interest is the Kube master output value. This will be the IP address that is assigned to the Kubernetes master so that we're able to log into it once the stack is created. Let's go ahead and use these templates to create a Kubernetes cluster. As I mentioned, some of the parameters are required. We can provide values for these parameters through the use of an environment file. An environment file is another YAML document with a parameters section, followed by parameter names and values. Here are the two required parameters, an SSH key name and a server image. We can see that this key name matches one that I have available in Nova. And we can see that the server image value matches the name of an available glance image. I've also provided a name server that I know is accessible from within my environment. And I've set an explicit size for the Cinder volumes that will be associated with each instance and used for Docker storage. We use the stack create command to ask Heat to create the stack for us. We provide it with the name of the main template, the environment file, and we give the stack a name. We can use the Heat stack list command to watch the status of the operation. When Heat has completed deploying our resources, this will read create complete. Heat has finished creating our stack. Let's see what we've got. We can use the resource list command to ask Heat for a list of resources that were created for us. Using Nova list, we can see our two Nova servers, the Kubernetes master and one worker node. We can use the Heat output show command to ask Heat for the IP address that was assigned to the Kubernetes master server. And using that, we can log into our environment and see what it looks like. We can log into the Kubernetes master as the minion user. Once logged in, we can see that we're running RHEL Atomic version 7.1.2. We can use the kube control command to interact with Kubernetes. For example, we can ask for a list of available worker nodes, and we see the single server that we expect to see. The Heat-kubernetes templates provide several examples in the etc Kubernetes examples directory. There are two types of files here, one service description and two replication controllers. A service is effectively a load balancer. It connects a network port to one or more pods providing a matching service, and then round robins between them. Let's go ahead and create this service. We can see a list of services with the kubectl get services command. We see two that are provided automatically by Kubernetes, and we see the web service that we just created. Within pods booted using Kubernetes, environment variables provide information about accessing these services. A replication controller creates one or more pods from a specified template. This example will create a simple web server serving static content. You'll note that the label here matches the selector that we saw in the service definition we loaded earlier. Let's go ahead and create this replication controller. We can use the kubectl get replication controllers command to see a list of currently running replication controllers. Here we can see the one we just created. But in kubectl get pods, we can see that this has resulted in a single pod running that has been scheduled on our one worker node and is currently running. We can run the docker ps command on our worker node to see the containers that resulted from creating that pod. We see two containers here. The first, running the pause command, exists only to provide a network namespace that will be shared by all of the other containers in the pod. The second container is our web server. We can ask Kubernetes to resize an existing replication controller with the kubectl resize command. Here we've asked Kubernetes to add a second web server pod. We see here that that has been scheduled on our worker node and is not yet running. But if we wait a second, it has started. If we rerun the docker ps command, we can see the second instance of the web server pod there. If we have a web browser that is able to access the Kubernetes service, we can see that it will round robin between the two different pods that make up the replication controller. The second example replication controller is one that will generate CPU load on our worker nodes. We'll use this to test out the autoscaling behavior of our heat stack. Let's go ahead and create that. Here we see that that has started a pod on our worker node. We should see the system load on that system start to creep up. It will take Heat a couple of minutes to respond to this change. We'll watch and see what happens. Looking at the output of Ceilometer alarm list, we can see that Ceilometer has noticed the change in CPU load on our existing server and has triggered the alarm. In response to that alarm, Heat has created a second Nova server for us. We can see that here in the output of Nova list. Returning to the resource list command, we can see that Heat is still in the process of fully configuring the new server. We see here that Heat has finished creating the new server. Let's log back into the Kubernetes master and see what things look like. If we ask for a list of worker nodes, we see we now have two. We're not yet running any pods on the new server. Let's fix that. We're going to add two more replicas to our web replication controller. We can see here these have been scheduled on the new server, but they're not yet running. It will take Docker a minute to pull the images down. If we log into the node, we can see that no containers have been started yet. You can see now that an IP address has been assigned to the first of the new pods. And if we run docker ps on the new node, we can see that the pods containers corresponding to our two new pods have been created. After a minute, we can see that both pods are now running. And if we run docker ps on our new node, we see the two sets of containers that we expect to see. That concludes this demonstration. I hope you found it both interesting and informative. If you have any questions, please feel free to let me know. Thank you very much.